So we have already talked about the fact that in our modern picture of gravity, which comes from Einstein's theory of general relativity, gravity is, either say it is or it is caused by. I prefer to say that it is. It is the curvature of space. The thing that we experience as gravity is objects that are following trajectories through a space that has had its geometry changed by the presence of matter. If you think of space as being kind of a uniform XY grid of points, that placing mass in that space, like a planet or a star or you, causes the geometry of that space to change. It changes the definitions of distances and times. And when we say curved space, I should actually be a little more careful and say curved space-time, because gravity also affects durations as well as distances. But it changes the definition of a straight line. So objects in space, when they travel a quote-unquote straight line, are traveling a straight line through curved space. And what we want to talk about today is what is the limit of that curvature of space? What happens if you put so much matter at one point in space that the curvature of that space becomes very, very, very large, and the amount of velocity you need to escape from that space becomes very, very big? What is the limit to that? The limit to that speed is the speed of light. And so an object that creates such a large curvature in space that nothing can escape from it is what we call a black hole. The Earth creates a curvature in space. When we draw these pictures of curved space, we often draw it as a two-dimensional sheet, as if space is like a trampoline with a heavy ball on it. That is an analogy to help our brains wrap around the idea of space being curved. The Earth is three-dimensional, space is three-dimensional. It curves space in 3 dimensions. So space is not a flat piece of fabric. Space is a three-dimensional coordinate system, and the presence of a massive object curves that space in all 3 of those dimensions. So this is a more realistic picture of what we mean by the curvature of space. We can see the curvature of space when we look at very, very distant objects where the light passes by something massive. We talked about the fact that the first evidence for general relativity, the first observational evidence for general relativity, was the fact that the sun bends the light of distant stars as that light passes by the sun. This was discovered way back in the early part of the 20th century, 1917, 1919 or so. This is a recent photograph from the James Webb Space Telescope from 2022. If you're watching this video in July 2022, this photograph is 3 or 4 days old. If you're watching this in 2023 or 2024, it's because I've been recycling my astronomy videos. But this picture shows a few stars. The things with the bright rays around them are stars in our own galaxy. You can think of them as kind of dirt on our glasses or bugs on our windshield. But everything else, all the distant objects in this image, are galaxies. And this one galaxy, well, you can see a lot of the galaxies appear as these long stretched out arcs, these long lines that are not little spirals or not little ovals, but are stretched into these long streaks. This galaxy in particular, if we zoom in on it, this is a spiral galaxy that is behind this galaxy. And its image is being distorted by the gravity of this galaxy as the light passes by, just like putting a lens in front of an image will distort what's behind it. The image of this galaxy is being distorted by the gravity of this galaxy curving space. You can see another long streak here of a galaxy whose image is being distorted. There's one there. So this phenomenon, which we call gravitational lensing, is observational evidence that Einstein was right, that light is bent by gravity, that a massive object will distort the path of light that passes by it. And nowadays we can actually use gravitational lensing. We can measure how much the light of this galaxy is distorted and use that to measure the mass of this galaxy. So general relativity is not only confirmed, it is a tool for astronomers to measure the masses of distant objects. So what would you need to do in order to make something curve space so much that nothing can escape from it? And when I say nothing can escape from it, that is based on the fact that there is another fact from Einstein's theory of relativity that says nothing can travel faster than the speed of light through space. The speed of light, 300 million meters per second, 186,000 miles per second, is a cosmic speed limit. It is physically impossible for an object with mass to go faster than the speed of light, because if it did, that object would have infinite energy, and it's impossible for an object to have infinite energy. If you look at Newton's law of gravitation, it says the force of gravity between two objects is the gravitational constant, G, 0.00000000000667, tiny number, times the mass of one thing times the mass of the other thing divided by the distance between them squared. You can use this formula to derive a formula for something called the escape velocity, the escape speed. How fast does something have to be going to get away from an object with a mass of m and a radius of r? So we took this formula and plugged in the mass of the Earth and the radius of the Earth. We would get the Earth's escape velocity. The Earth's escape velocity is about 11 kilometers per second. That's how fast something has to be going to go away from the Earth and never come back. Notice that the little m is gone now. The escape velocity of an object doesn't depend on its mass. If I wanted to throw a baseball to the moon, it would have to be going the same speed as shooting a rocket to the moon. You might say, that doesn't seem right. Well, it's harder to make a rocket go that speed, 11 kilometers per second, than it is to make a baseball go that speed. But the speed it has to go to get there is the same. The kinetic energy it has to have. Or the ratio of kinetic energy to potential energy. We won't go into how this is. If this was a physics class, we would derive this formula. It's not a physics class, so we don't have to derive. We just have to understand it. One of the things we have to understand is that an object's escape velocity depends on its mass and on its size. If I took the Earth and I somehow squeezed it down to half its size without changing its mass, I just compressed it, the force of gravity, we feel, would be bigger. It would be 4 times bigger if we made the Earth half as big. And it would be harder to get off the Earth if its radius was smaller, because we would be closer to more of its mass. Right now, when I stand on the Earth, some of the mass of the Earth is really close to me, the dirt under my feet. But some of the mass of the Earth, the rocks that make up Australia and the rocks that make up Antarctica and the rocks that make up Africa, are far from me. If I make the Earth smaller, all of that mass moves closer to me. So the gravitational force that the Earth exerted on me if I squished it would be bigger. So it would be harder to get away. The escape velocity would go up. So there are 2 things that affect how much gravitational pull something has. How much mass it has, and how small of a size that mass is squished to. If you ask how massive or how small would something have to be to have an escape velocity equal to the speed of light, you just plug the speed of light into this formula and you rearrange it, and you get a formula for what we usually express this in terms of the radius of the object. For a given mass, how small would it have to be in order for its escape velocity to be c, the speed of light? This size is called the Schwarzschild radius, because the person who first calculated this was Carl Schwarzschild, using Einstein's equations, not using Newton's laws like I did. That's cheating, but you actually get exactly the same answer, which is super cool. This is the kind of stuff that happens in physics that makes physics really interesting. If you calculate how to make a black hole using Newton's laws, and you calculate it with Einstein's theory of general relativity, you get the same expression for the Schwarzschild radius. It's really interesting. So this is how small do you have to make a mass, a given mass, to make it a black hole. You can make anything a black hole if you squish it small enough. Every object has a Schwarzschild radius. The sun is a great big star. If I squished the sun to a smaller object, it would become a black hole. The escape velocity on its surface would be so big that you couldn't escape from it. That radius is about 3 kilometers. If I squished the sun to a little ball that was 3 kilometers in radius, that little ball would be a black hole. The Earth also has a Schwarzschild radius. If I took the whole planet Earth and squished it to 1 centimeter, about the size of a marble, that object would be a black hole. It would be a black hole with the mass of the Earth. If you got really close to that black hole, you wouldn't be able to get away again. You have a Schwarzschild radius. Your Schwarzschild radius, if you weigh 80, 90, 100 kilograms, is 10 to the negative 25 meters. That is 1/10 of 1/trillionth of 1/trillionth of a meter. If I could somehow take all your atoms and molecules and squish them down to, that's about as many times smaller than a proton as a proton is smaller than you. So if I took all your atoms, squished them into a proton, and then did that again, you would be a tiny little black hole. Now that doesn't mean you have more gravitational pull than you had before. It just means that it is possible to get very close to all that gravitational pull. This is an important thing to remember about black holes. They just have gravity. They aren't kind of magic cosmic vacuum cleaners. If I somehow took the sun right now and squeezed it down to a 3-kilometer ball, 3-kilometer radius ball, it would be a black hole. It wouldn't give off light anymore because light isn't going faster than a black hole's escape velocity. But the Earth in its orbit around the sun would keep orbiting that object just like it had before. It wouldn't suddenly get sucked into the black hole. It's orbiting an object with a mass equal to the mass of the sun, and it would keep orbiting that black hole with the mass of the sun. It would get cold and dark because no more light would be given off, but the gravitational pull of the black hole wouldn't change. What makes a black hole is you can get very, very close to it. You can get very, very close to all of its mass. And the closer you get, the greater that escape velocity gets until it reaches a point where it exceeds the speed of light. So a little black hole vocabulary. A black hole is a region of space. As you get closer and closer and closer to that region of space, the escape velocity gets bigger and bigger and bigger. There is an imaginary line in space where if you are outside of that imaginary line, the escape velocity is less than the speed of light. If you had a very powerful rocket that could go half the speed of light or 80% the speed of light or 90% the speed of light, and you were at this point in space, you could escape from the region around the black hole. But if you cross this imaginary line, you enter a region of space where the escape velocity is greater than the speed of light. No matter how powerful your rocket ship is, you cannot escape from that region of space. That imaginary line is called the event horizon. The event horizon means that any event that happened on the other side of that line, we could never know anything about because light cannot travel from this region of space to this region of space. It is cut off from our universe. In fact, it's arguable that you could call the region inside of a black hole's event horizon a separate universe from ours. Why? If what you mean by universe is anything you can possibly observe, you can't possibly observe anything inside the event horizon of a black hole. Is it part of our universe or not? Well, it exerts gravity in our universe, so this thing, whatever it is part of our universe. But this region of space is forever inaccessible to us because it exists in a place where we can never know anything about it. It raises a lot of interesting philosophical questions about what it means to be able to make a scientific statement about something. Can we make scientific statements about what happens inside of a black hole event horizon if we can never even potentially observe the space inside of a black hole event horizon? Maybe not. But the event horizon is not a solid wall. It is not an object. It is not a physical object that is the surface of the black hole. It is an imaginary line that delineates the part of space inside the black hole and the part of space outside the black hole. I don't know what's next. Oh, what's inside? What's inside that? What is the black hole? Remember, what are we talking about here in terms of where does this idea come from? Where the idea came from in the first place was you've got this collapsing core of a star that's about to go supernova. The core collapses. It compresses matter to iron nuclei, to neutron star density. And if it's massive enough, it can keep squishing those neutrons away smaller and smaller and smaller. And when we talked about that collapse and we talked about what happens if a neutron star is so massive that the gravitational force squeezing it in is stronger than the ability of neutrons to withstand that compression? What happens? And the equations of physics say, well, gravity will just keep squishing that thing. It'll squish those neutrons together until they're quarks, and it'll squish those quarks together closer and closer and closer together until the whole object has a size of 0 meters, 0 centimeters, 0 inches, whatever you want. In other words, it goes away. It still has mass, but it has 0 volume. We call that situation. I'm not going to call it an object because I'm very fussy about this word. The singularity of the black hole. The singularity of the black hole is the mathematical zero-dimensional point that the laws of physics say all of the matter of that star will collapse to. And it's located at the center of the event horizon. But what is this singularity? How should we think about it? It helps to understand where the word comes from. The word singularity comes from mathematics. If we take a mathematical function like y equals 1 over x, we can make a graph of it. I can take any x and plug it into this mathematical function and get a y. If x is 1, y is 1. 1 over 1 is 1. If x is 2, y is a half. 1 over 2 is a half. If x is 10, y is 1 over a 10. That's a tenth. If x is a quarter, 1 over a quarter is 4. So here on the graph, here's a quarter, 1 over a quarter is 4. And I can make a graph of that function. I can plug negative numbers in too. If x is negative 5, y is negative a fifth. So this function, this mathematical function, y equals 1 over x, is fine, unless you try to plug in x equals 0. If I plug in x equals 0 for x, I get y equals 1 divided by 0, and 1 divided by 0 is not a legal mathematical process. You can't do that. It's not allowed. If you pick up a calculator and type 1 divided by 0 equals, your calculator will say error, or it will say not a number, N-A-N. Why? Because if 1 divided by 0 equaled something, that would mean that something times 0 equals 1, and that doesn't make any sense because everything times 0 is 0. So you're not allowed to divide by 0. Dividing by 0 is a illegal mathematical operation. In mathematics, the way we describe the situation of the function y equals 1 over x is we say the function y equals 1 over x has a singularity at x equals 0. Or the point x equals 0 is a singularity of the equation y equals 1 over x. Or the function y equals 1 over x is singular at x equals 0. It doesn't have a value there. Now, you can cheat a little bit. You can say, well, look, what if x is a tenth? Y is 10, right? 1 over a tenth is 10. What if x is a hundredth? 1/100th, 0.001. 1 over a hundredth is 100. What if x is 0.00001? 1 millionth. 1 over that, y is a million. The smaller x gets, the bigger y gets in this function. If x is a billionth, y is a billion. If x is a trillionth, y is a trillion. The closer you get to x equals 0, the bigger y gets. It's tempting to say that 1 over 0 is infinity, because as you get closer and closer and closer to the axis here, this number gets bigger and bigger and bigger and gets as big as you want it to be. Well, infinity is not a number. You can't really say that. You can't say 1 over 0 is infinity. You can say the limit as x gets closer and closer to 0 gets closer and closer to, well, it doesn't get closer to infinity. You can't get close to infinity. As x gets closer and closer to 0, y gets bigger and bigger and bigger without bound. And an unbounded number is infinite. But we have to be careful. If we make the same equation, y equals 1 over x squared, this is like the law of gravitation, right? The force is equal to 1 over the distance squared. As you get closer and closer and closer to an object, if it's small enough, that force gets bigger and bigger and bigger and grows without bound. But it's important to understand that this word singularity in mathematics means a place where a function is undefined. The function does not give you a number as an answer. It gives you an error as an answer. So what is happening at the singularity in physics and astronomy is we are asking our equations of physics, what happens if the density of matter and the space-time curvature are so great in a black hole that you've got 3 stars worth of mass on a kilometer worth of space? What will happen to the density of matter in that space? What will happen to the space-time curvature in that space? And our equations tell us that the density of matter is infinite. It is a star's worth of mass in 0 space. Or the curvature of space-time at that point is infinite. Well, we shouldn't take that seriously because infinity is not a number. It is a calculator error. What's happening here is our equations of physics are unable to deal with that much matter compressed into that small of a space. They're unable to give us a reasonable answer for what happens if you put a star's worth of mass into a baseball-sized amount of space. What it says is, oh, that thing will just disappear. It'll keep going, it'll keep getting smaller until its size is 0. Well, something with mass can't have a size of 0. That doesn't make sense. How do most scientists interpret this situation? The way most scientists interpret this situation is to say, we have got this theory of gravity called general relativity, which explains very well how very massive objects curve space. We've got this completely different theory called quantum mechanics or quantum field theory, which explains the interactions of little tiny subatomic particles, neutrinos, electrons, quarks, etc. We are asking physics what happens if you take so much mass that it curves space into so small a space that you have to use quantum mechanics to describe the interactions of the particles. And the answer we get is essentially nonsense. It is not an answer. Most physicists see this as evidence that general relativity and quantum theories are incompatible with one another. They don't play nicely together. This singularity is a signpost to the fact that we probably need a new kind of physics that can describe very massive objects that are on the quantum scale, that are the size of protons and atomic nuclei. And we don't have that. We've got quantum theory, which we came up with to describe particles, and we've got general relativity, which we came up to describe huge, massive objects in space-time. And right now, they're not working together to give us an answer that's sensible. You will hear physicists, cosmologists, astronomers talking about a singularity like it is an object. It is an object with infinite density. Be really mindful when you hear astronomers talking that way, because they are being sloppy and not always clear about what that means. We don't really know what happens at a singularity because we can't really use our equations of general relativity and quantum mechanics to address the same system. You may hear physicists talking about the need to come up with a unified theory or a theory of everything or a grand unified theory. What they are talking about is coming up with a theory that can deal with both quantum systems and massive systems and curved space-time all at the same time. If you've ever heard of string theory, that's what string theory is trying to do, and kind of failing, by the way. Quantum gravity. These theories don't exist yet, or at least working versions of the theories don't exist yet. But we think they're what we need to do to make the singularity, whatever is going on there, give us answers that are not just 1 divided by 0, because that answer does not make any sense. Now, that's not to say we don't think black holes exist. We do think black holes exist. But the idea of a black hole poses a problem if we want to verify that they are real things that happen in the universe. It's one thing to be able to write down on a piece of paper, hey, look, Einstein's theory of general relativity can give us this mathematical object that has an escape velocity greater than the speed of light. That doesn't mean they're real, just because we can write down an equation for it. Sure, if we took the Earth and we squished it down to the size of a marble, it would be a black hole. But can we imagine anything squishing the Earth down to the size of a marble? No, not really. If we took the whole sun and squished it down to the size of a city, it might be a black hole. Can we imagine something that would squish the sun down to the size of a city? Well, kind of. That's kind of exactly what we say happens in the core collapse of a very massive star. A star's worth of mass being squished into a few kilometers. So we think that that process might actually happen. But there's no way to be sure unless we actually go out and see one. And hopefully you can see how that is a problem, because the whole point of a black hole is that no light can escape from it. If there was a black hole in the universe sitting all alone by itself, there would be nothing to see, because by definition a black hole doesn't let any light escape from its event horizon, because the escape velocity of the event horizon is greater than the speed of light. Nothing can escape from the event horizon, so how could we see it? The answer is we couldn't if it was just sitting in space by itself, but we don't necessarily always expect a black hole to be sitting in space by itself. If a black hole is located near other material, that material will be orbiting the black hole. It might be orbiting the black hole very fast, because the gravity when you get close to the black hole is very big, and that material could be very energetic and very hot. So we cannot observe a black hole directly, but we certainly can observe the effect that a black hole is having on its surroundings because of its very large gravitational pull. This is an artist's conception. This is not a photograph of material orbiting around a black hole. Here's some stars that have gotten pulled apart by the black hole's gravity. There's these jets that shoot up the north and south poles of this, what's called an accretion disk. The black hole is accreting or piling up material through its gravitational pull. As it spins around, friction will cause it to heat up. Charged particles moving in a circle will create a magnetic field. That magnetic field will create a hot spot at the north and south pole, just like a rotating neutron star, and that will cause the region north and south of the accretion disk to be more energetic, which will cause energy to stream out preferentially in those directions. If a black hole has an accretion disk, we might be able to observe either this very hot material orbiting the black hole or these jets of material emitting from the hot spots in the magnetic field. Can we? Do we? Again, this is an artist's conception of what one might look like. So what are we looking for when we're looking for a black hole? We are looking for, first of all, something with a lot of mass in a very small space. I don't know where my... Okay, so what are the telltale signs of a black hole? We could see a star, this blue supergiant star, orbiting around something that we can't see, something small and massive in space. So we can see something orbiting a black hole, even if we don't see the black hole. If this is orbiting something very massive and very small, we might conclude that that thing, whatever it is a black hole. We can also imagine very large amounts of energy, X-rays and gamma rays, from this very hot material spiraling into the black hole, coming from a very small space. If you've got enough energy in a small enough space, that thing with that much energy in that small space could be a black hole. We have seen objects like this before. The first one, Cygnus X1, was observed way back in the late 1960s. We have known for almost my entire life that black holes are probably real things in the universe. Stellar mass black holes, though, black holes caused by the collapse of a single star, are actually pretty hard to detect because they have to be formed in somewhere where the black hole is having some kind of effect on an object nearby. But we do think that these black holes exist. The evidence for black holes actually comes from black holes that are not just a single collapsed star, but something called, I don't know what's with me, my clicker today, supermassive black holes. Supermassive black holes are found in the centers of galaxies. This is a spiral galaxy. It's actually a barred spiral galaxy, which probably doesn't look too terribly different from our own Milky Way. This is a visible light photograph of that galaxy. This is an X-ray photograph of the very central region of that galaxy. And when we look at the very central region of that galaxy in X-rays, remember X-rays are at the shortest wavelength, highest frequency, most energetic end of the electromagnetic spectrum. We see something very small and very bright in X-rays with this region of material around it. So at the center of this galaxy, there is something very small giving off huge amounts of energy. The size of this thing is usually smaller than our solar, or about the size of our solar system. Does that prove that this thing is a black hole? No. What it proves is at the center of this galaxy, there's something very small, very massive, and very energetic. Here's another galaxy. Okay? Again, in X-rays, the center of this galaxy is something small, dense, with a disk of material orbiting around it, giving off X-rays, very energetic radiation. Does that prove this is a black hole? No. But what it suggests is the center of this galaxy also has something very small, very massive, and very energetic. So small and so massive and so energetic that if it's not a black hole, we don't know what it is. So our best guess is that these objects at the centers of these galaxies are black holes. If we measure the orbital speed of the stars in the very middle of the galaxy, they are orbiting very fast. In order to be in an orbit that's very fast, there has to be a very strong force holding you in orbit. The mass of these black holes at the centers of galaxies is not just the mass of the sun, or 5 solar masses, or 10 solar masses. These are called supermassive black holes because they have masses of tens of thousands, or hundreds of thousands, or millions of times more than the mass of the sun. Now, there are no stars that are a million times more massive than the stars. So whatever these things are, they're not just a single collapsed star. They are something else entirely. Here's a picture of a galaxy in visible light. It's just a large elliptical galaxy. It looks pretty much like a uniform ball of stars, probably a trillion or so stars. If I take a picture of the same galaxy with a radio telescope, it looks like this. There is something shooting light, radio waves, out of this galaxy over hundreds of thousands, maybe even millions of light years of space. If I zoom in on the center of this galaxy with a radio telescope, I see this. Something very small, very dense, with a ring of material orbiting around it. That has got to be a black hole. If it's not a black hole, we don't know what it is. We can't think of anything else that would be that massive, that small, that dense, and have stuff orbiting around it that fast. So this is the evidence for supermassive black holes at the centers of galaxies. More recently, we have developed the technology to take a picture of the region around the event horizon of these supermassive black holes using radio telescopes. The Event Horizon Telescope is a radio telescope. This was the first quote-unquote picture of a black hole. Now, what is this really? This is a map of the radio waves being emitted from the center of a galaxy. It's not exactly a picture, right? Because radio waves aren't exactly the kind of light we can see. This is a radio wave map translated into visible light that we can see. This region in the center is where the black hole is. The reason it is black is because you cannot see light coming from inside the event horizon. This light here is actually light from behind the event horizon that's being gravitationally lensed and bent over the black hole. If you've ever seen the movie Interstellar, the black hole in that movie is an artist's conception developed in consultation with cosmologists and physicists and astronomers who study black holes. It's a realistic depiction of what it would look like to look at the event horizon of a black hole in visible light as we could come up with. So you're seeing the black hole, but you're also seeing light from behind the black hole being bent around the black hole. So it's like looking at a three-dimensional distortion of the event horizon, or of the accretion disk orbiting the event horizon. This is the first picture of the black hole at the center of the Milky Way galaxy. Our galaxy also seems to have a supermassive black hole at the center. The object that contains that black hole is called Sagittarius A. We've known for decades that is a place where a lot of energy is being emitted. This is, again, an image with a radio telescope of the region around that. You can see that not much light is being emitted here. That's where the black hole is. This is the accretion disk. These three hotspots are actually triple images of the same part of the accretion disk. The distortion of the light coming around the black hole caused by the black hole's mass is what creates this sort of triple image. So again, is this a photograph of a black hole? Not exactly. But it's the best we can do, given that you can't see the center of our galaxy with visible light. Visible light is blocked by the gas and dust in our galaxy. We can't see Sagittarius A with a regular telescope. We can't see what's in the middle of it because that visible light is blocked, but the radio waves get through. So this is a radio wave map of the region around the center of our galaxy, and what we find is exactly the kind of optical distortion we would expect by a very massive object curving space-time. There is very little doubt in the mind of any astronomer that the centers of galaxies contain these things called supermassive black holes. What are they? That's a really interesting question, right? They're not just a single collapsed star. What could they be? Well, it could be that over time in the history of a galaxy, lots of stars go supernova and leave behind black holes. It could be that those black holes merge together and get bigger and bigger and bigger. And in the center of the galaxy where there's more stars, they've grown into this big black hole that consists of hundreds of thousands of smaller black holes that have been swallowed up together. That could be. It's probably not. The other possibility is the supermassive black hole was here before our galaxy was here. In other words, the supermassive black hole formed first, and it's the gravity of the supermassive black hole that drew together the material that would become the galaxy just a few million years after the Big Bang. So the supermassive black hole could be the seeds around which galaxies formed. Do we know for sure the history of supermassive black holes in the centers of galaxies? No, we don't. It's a super interesting current area of research. It's something we're trying to figure out. And these sorts of images of supermassive black holes are a big step towards being able to answer those questions. These are only, like I said, this is a picture from earlier this year. These are brand new discoveries. I said that our current theories can't completely describe what's going on at the center of the event horizon. They can't completely describe the singularity. It doesn't stop people from speculating about black holes. I'm not going to go into a whole bunch of the what happens if you fall into a black hole stuff. I'll try to find you some good videos of that kind of stuff. But questions about what is inside the event horizon are interesting, but at this point in time, not completely answerable. There's even speculation that a black hole could connect different parts of space-time to one another. That a black hole at this point in space-time and a black hole at this point in space-time could be connected together by a passage through space-time called a wormhole. Probably not. Wormholes are probably just things that exist on paper. I can write down the equation for a wormhole in an empty universe, but as soon as something goes into the wormhole, that something's gravity curves space-time in the wormhole and it pinches it off and it stops existing. Wormholes are great for science fiction because they let you travel from one place in the universe to another place in the universe without breaking the speed of light. They're not exactly impossible, but they're probably not real, as opposed to black holes, which are not only possible, but probably real. So thinking about black holes brings us right up to the very edge of our understanding of mass, space-time, and physics. And we think that that understanding is just a little bit incomplete. And so maybe in your lifetime, we'll come up with fully unified theories of gravity and quantum mechanics, and we'll have no more unanswered questions about what goes on in the singularity of a black hole. But for now, we have to live with some unanswered questions about black holes. What's going on at the singularity? Not sure. Are wormholes real? Not sure. But that's okay. As I've said a few times, I think already in this course, unanswered questions are not a bad thing in science. Unanswered questions are the raw material for scientific advancement. And so every unanswered question about black holes are probably going to result in new theories, new ideas about space-time in the next 10, 20, 50, 100 years.